Hello, this is Britt Caswell with another example video. In today's video, I'm covering example 1 from section 6-3 in the SavvasRealize Algebra 1 textbook. So the goal of this example is to understand exponential growth and to try to apply some real-world situations to it. All right. So we learned yesterday that well, I shouldn't say yesterday, I should say in our last video. We learned about this equation here, where A is some kind of initial amount and B is our constant ratio. So now we are taking that equation and we're expanding upon it. We are saying that our constant ratio in this case is 1, meaning 100%, plus some kind of growth rate. Now understand, this could also become some kind of decay by having that rate be a negative value. Okay, so it could be a subtraction of r here as well. All right. Now, exponential growth is used for a lot of different things. All right. We look at it with money. We look at it with population. We look at it with viruses, such as the COVID-19 virus going around. We use it for like bacterial growth. We can use exponential decay to talk about the amount of medicine still in your blood system, like in your bloodstream. So we can use it in pharmaceuticals. We can use it to discuss radioactivity and half-life. All right, so exponential growth and decay isn't just a money thing, but it is kind of everything, and it's all of our really important stuff. So understanding how exponential growth and decay works is going to be really big, especially for you in your personal life when you think about investing. So, I'm going to get off my soapbox and let's talk about this word problem. So there's a town, it's called Hillville, all right, and they have a population of 5,000 people, according to their little sign. And it says that every year, the population of Hillville is growing at a rate of 15%. And they are wondering, what will the estimated population of Hillville be in 5 years? So most of these growth and decay problems are really just saying what your values are and plugging them into the formula. So let's go ahead and let's do that. All right. Now our A value stands for our initial amount. All right. It's our starting population. It's how much money you deposit into your bank account. It's how many bacteria there are. Okay, so that's our starting whatever we're looking at. And then inside the parentheses, we have 1 plus, it's a plus because we're growing here. The town is getting larger. And it's growing at a rate of 15%. Now remember, if we go to put a percentage inside of an equation, you have to convert it to decimals. So this is going to be 1 plus 0.15 here. And then our x, which happens to be in our exponent, is talking about the amount of time in years. So this word problem is asking us about 5 years. So I am technically finding f of 5. All right, so now that we are at that point, let's take it a step further. So when I go to simplify this, the first thing that I do is I actually clean up those parentheses. All right. Now understand, I cannot multiply this 5,000 and the stuff that's in the parentheses until I have raised it to the exponent. Okay, so that 5,000 and that 1.15, those cannot be merged until I have dealt with the fact that the 1.15 is raised to the 5th power. So now if I was using a cheap scientific calculator, okay, what I would do is I would take the 1.15 and raise it to the 5th power, and then I would multiply it times 5,000. However, Desmos.com gets a free plug from me right here. This is what I use to This is what I use to actually do my calculations. So I'm doing 5,000 times 1.15 to the fifth. And so what I'm looking for is I'm actually looking for perhaps some kind of line. I think I might have to put a y here. Ah, there we go. It actually tells me in the box. So inside my box, I get 10,056.78. So I'm going to write that out. So again, 10,056.78. And I have to ask myself, can I have 0.78 of a person? No, that would be terrifying. So instead of calling it 56, I'm going to call it 57. And that would be my population in 5 years. So now let's talk about the second situation. All right, there's another town called Valley Town, which also has 5,000 people in it. Now, these 5,000 people, they are having an extra 1,000 people come and move in with them every year. And in this problem, they're wondering, can the expected population for Valley Town be modeled with an exponential growth function? The answer in this case is no. All right, exponential growth requires a growth rate, which is some kind of set percentage that the town grows by. In this case, there's not a set percentage that it grows by, but a set number of people. And that number of people is neither the A or the R value. Instead, this town, Valley Town, would grow very similar to a linear graph, where you start at 5,000, and then every year you grow by another 1,000. So it would grow linearly like that, as opposed to Hillville, which is growing exponentially, which would look something like this. So there we have it. That is exponential growth and decay when we're talking about population. Until next time.